So we shall carry on. Now, the next agenda item was not to go straight to a talk, but Bertie asked me to look at a diagram he produced, which is this. Now, when I say produced, actually what happened was that I have sent to the organisers some scans. Now, hang on, where is that? That document I scanned. Oh, yeah. A series of pages, 7 or 8 pages from the excerpts from the original book, which were in the 40-year retrospective book. Now, this is the scan that this is from the scan that I sent, and then Bertie produced a high-quality version of it. Now, however, Bertie, I think there's a copy and paste error in your production, which is you've got immediately leaving familiar aspects, immediately having familiar aspects to guide students, and immediately having familiar aspects to guide actions. Oh no, so the same thing, I think, in both boxes, isn't it?
Yes, it's a copy, paste, and paraphrase error. So we will fix it. I will fix it in that regard and send it out again.
Am I sharing the screen still? I'm not sharing the screen, am I?
Yes, you are not now. I will quickly fix it, and then we can share it from that one. I'll do that just now.
You can. How about would this work, Bertie? In the interest of, can I just go to my scan and just work off that? Or?
Yes, no problem. That's fine.
And you're seeing that right now, aren't you?
Not yet, no.
Not yet.
Seeing the chat screen, the interface off. So maybe just share the screen again.
Oh. I'll try. Am I sharing the screen now?
Yes, that's fine.
And people are seeing a page which starts with page 22, excerpts from the handbook. Is that right?
Yes.
Good. So Bertie wanted me to go through, and I'll confess, Bertie, and you shouldn't be embarrassed by this, that I think I'm about to be embarrassed because I've never quite understood this diagram. I know of these very violent annotations on the are mine. So fairly clearly I've spent some time looking at this, but I'm not always sure that I understand what it's trying to tell me. So particularly amongst the organisers, if it's speaking to you in some way, feel free to pipe up as we go through this with your possibly better interpretation. I relate better to the words in Bloom's book than this particular diagram. So a problem is presented, an exam question is presented, and then I think this is key. It comes down to, I've talked a lot about, oh, well, we haven't talked about it. Let's see. Then the question is perceived in one of 2 ways, if you like. It seems to be unfamiliar is one of the possibility, which would lead the student to trying to find bits that they do find familiar. And then otherwise it's immediately obvious that it's familiar. It has familiar aspects to guide actions. So then we move down. So let's move down to here. So staying with the familiar, some restructuring by student to make resemblance to familiar model more complete. Okay, so I think the point that Bloom is trying to make is that, it doesn't. Some work may be required by the student to turn into something that feels familiar. And then initially unfamiliar, there's a process the student has to go to where they the student uses familiar elements to restructure the problems in a familiar context. And then they come back together again. So I think what we're saying is, what's the student's initial reaction? Whatever, one of 2 things, but nevertheless, the student has managed by either of these processes to arrive at a point where they feel that the problem they're being faced with is of a familiar type. Now, I wrote over here, as you can see in my annotation several years ago, application starts here. I'm not sure what I meant by that. So I should leave that out now for the moment until I figure it out. Maybe I will as I go through more of this. So then, selection of abstraction, theory, principle, idea, method suitable to problem type. Now, I'm not sure why I drew that. This application starts here. I don't know why it's so high on the page. Right now, I'm thinking that actually that annotation should be down here. Maybe it was meant in a sense to be down there in the sense that it was It was talking about everything above that big thick line. Here's the crucial step in application. The student had to make a selection of an abstraction, a theory, a principle, an idea, a method to solve the problem. And that's the key difference from comprehension or understand. All the information was provided in the comprehension understand question, whereas here the crucial step, this is maybe why that application starts here, the crucial step happens where the student must make a decision about what theory or principle idea they're going to use to solve the problem. And then I said here, difference comprehension starts at step 5. I'm not sure why I wrote that. So Bertie, in your change, maybe you should take out my annotations. I'm not sure what I mean by them now. If they speak to you, keep them in. Use of abstraction to solve the problem. So the student has made the selection, and then they've solved the problem using that abstraction, and they have their they start to solve it and they solve the problem. So there's the diagram. Anybody want to comment upon that? Let's start with the organisers. Any comments, guys?
From the chat, Ronnie commented on use the I don't know if it's Cinefin or Sonefin mode. Maybe, Ronnie, you can just elaborate a little bit more.
Yes, it's Cynefin. It's a Welsh word meaning family. If I can share my screen, then I can quickly show it to you, and then maybe we can use that to understand this diagram a little bit better.
Okay, I think I've stopped sharing, so you should be able to share.
Okay, so this is Snowden, and we extended on it in a recent article that me and a colleague published. So these are the different quadrants that we operate in. So once you are confronted, there's a kind of a disorder where you don't know, it's this one, 0, which is this little block here. Mm-hmm. Let me see if I can quickly just add this, and it's easier for me to. Sorry about this. This area here, where you don't know in which one of the spaces you are confronted with this uncertainty. Then you have to decide whether it's known, whether it's chaotic, whether it's complex or noble. And then there's a set of best practices for each one of these ones. So in the known one, you'll select the best practice. In chaos, you will have some trial and error type of action. In this one, you will have a fail-safe experimentation, and in this one you have critical thinking. So if one can apply this to that diagram of yours, I think it might be easier to understand how it flows.
Okay, so we put that diagram that you said. Well, actually, we've got a little problem now, haven't we? We probably need both.
We can't share both, yeah, unfortunately.
Yeah.
I will share this with Joey, and then she can send it to you or something like that.
Okay.
I think that is a good idea, Ronnie, that we can just put it next to each other when he projects. While you're sending it, there's Donald also wanted to contribute, so we will just give Donald a chance to contribute while you send us that diagram that we can share it together next to each other by Prof. Lister. Donald, you can talk.
That might have been an accident, sorry.
We have a comment. In looking at the original order diagram, doesn't it mean that for comprehension, the first steps are provided as we look in those steps in the diagram? And that is how we understood it, as I also understood it when I've gone through it.
That sounds familiar.
I think it comes.
That sounds very plausible to me, because I think that's how I was. Did that come about because not only did you look at the diagram, but you were reading the text at the same time?
Yes,
Is something that?
Yes,
Yeah.
and I think you mentioned it. I can't put my finger on it now. In one of your previous articles as well, that it is like a flow. But don't ask me to pull it up now.
Okay. Yeah. Okay. So where do we go from here? Are we waiting for something where the two things we put together? By the way, if we're going to do that, I shall warn the person who shared that diagram that they are going to have to talk about the relationship between the two diagrams, because it's there. I'm still processing their diagram. I wouldn't dare attempt to relate their diagram to this. They will have to do the talking.
Now, I think, Prof, you can continue with your normal, the type of presentation, and we can take questions at the end again. And then later on, we can maybe arrange like an informal discussion where we can sit with Ronnie, because it's obvious that he's also done some wonderful research, and then we can discuss it in an informal manner at a later stage. And then Ronnie can share it with us again. So let you continue with your presentation. And then Ronnie says, that's fine. So then we listen, and you can continue as you planned.
Okay. Right, I'm going to share the screen, or attempt to. And if I've done it right, you should be now looking at a page which has a wonderful picture of some good-looking man, and then it says at the top, talk 3. Is that what people are seeing?
Yes, Prof.
Good. Okay. A little. Oh no. So talk 3 was advertised as following, as having Piaget theory and teaching practice. To some extent, it should be Piaget theory and also teaching practice. So there's sort of kind of two parts. They're related, but they're somewhat disjointed. And we'll see how we're going. I mean, I noticed that we're now almost at the half-hour point, half past the hour. If I give this whole talk, it could last an hour, which may leave less time than the organisers would like. I could just do a portion of it and leave the rest. How about I start, and we'll get to the hour. We'll get to in about 35 minutes, we'll get to the top of the hour, and maybe then the organisers can decide for themselves whether they've heard enough of me or whether they think I can carry on. So let's get going then. So talk 1 was the early stage of my career in the development, a lot of it before I actually started doing research. And then I became this research evangelist in my middle years, and I talked about that yesterday. And I guess I remain the evangelist in the latter stages of my career, and that's what I'll talk about today. A lot of this actually is not till 2020. It's probably stopped around 2000. We'll stop with Donna's thesis really, and Donna Teague's thesis, and we'll get to that shortly. So where did we finish yesterday? I made this connection, but that we didn't have to approach research and teaching as two separate worlds. We could combine them, and I'm not going to go through all that. I just want to remind you of a saying that I've had on several slides yesterday. A good exam, or any other assessment item, but a good exam should teach you something new about your students, and what you learn that's new from your exam or your other assessment item should then be used to drive change in the subject in the future. And yesterday, actually on Monday and yesterday, I went around this cycle 3 times, and I won't go through a detailed summary of all 3 again. I think I'll just remind you of what had happened by the end of the 3rd cycle. By the end of the 3rd cycle, we were talking about this sort of data analysis where in a final exam, some colleagues, Anne Venables and Grace Tan, put some exam questions into their final exam, some questions which involved tracing and some questions that involved explaining. And we wanted to see how students' performance on those 2 types of questions predicted their performance on writing. Predict, I shouldn't use that word. In what way is tracing, explaining related to writing? Do they correlate? And I asserted yesterday that that's a really good fit. And I won't go through the entire defense, but I'll just point out again that nobody who did poorly on both tracing and explaining, none of these students down here who did poorly on tracing and explaining did well on writing. And equally, nobody who did well, or Nobody who did well on tracing explaining did poorly on writing. So on that basis, this is really a different diagram representing the same thing. We were arguing by the end of that work that somehow, some ability to trace code and some ability, when I say explain, I mean, it doesn't have to be an explaining plain English question. It could be any technique you use to establish that a student understands a piece of code. So, but I use explaining because that's the sort of questions we use. So if a student can trace the code, and if they can demonstrate some ability to understand a piece of code, if they have those two skills, it tends to predict quite well whether they'll be able to also answer writing questions well. Now, the issue in those first 3 trips through the research cycle was that although we did some, I like to think, was nice empirical work, putting questions in the end of exam papers and so on, there was no real theory guiding us. It was just our gut instincts as teachers, very experienced teachers, and I'm not taking all the credit for this. There were some very talented people in the group. The idea of an explaining plain English question came from somebody else. The specific one that we used a lot, the code that checks to see if an array is sorted, was suggested by somebody else again. So I'm not taking all the credit for what went on. But there were good guts involved, people with good intuitions about their teaching, and that led us partly by luck, experience, good intuition, and some luck to use good questions. But the trouble with relying upon that all the time is, and no real theory, is that your luck will run out, your intuitions will run out. You need some theory, and as Kurt Lewin said a long time ago, there is nothing so practical as a good theory, because a good theory will help us guide us asking our next question and driving our next trip, next few trips through this loop. I should say in this sense, it's not that there is no theory. Really, everybody's walking around with a theory in their head. They're just not aware of it. You've always got a theory. You're always being guided by a theory, but you just don't know what it is sometimes. So what I'm going to do is I'm going to talk about the 4th trip through. And this is where Donna Teague, my ex-PhD student, and I applied Neo-Piagetian theory. One thing that's not clear here is that neither Donna or I invented Neo-Piagetian theory. It dates back to the 1980s. We read about it, we liked it, and we applied it to programming. We were the first people to apply it to programming, or at least in this form. Furthermore, I'm so aware that my talk ran over time yesterday that I'm going to try to, I could talk for several hours about Neo-Piagetian theory and how it applies to programming, but I'm going to try to just give you a taste. I'm not really going to talk a lot about it. Just give you a taste. So here, there's a picture of Donna, my former PhD student. She submitted her PhD thesis that you see Neo-Piagetian theory and Novice programming. She submitted that in 2015. So the theory she used was Neo-Piagetian thinking. And the empirical method was think aloud. Somebody, I think yesterday, asked a question. They said, you've got all these quantitative results. What about qualitative research? And my answer to them was, well, wait till tomorrow. And here we are. Yes, we'd got some good results by sitting down by putting questions into exams and then sort of interpreting at a distance, looking at the exam paper and thinking about what we thought that said about the students' thinking. Well, Donna went much more direct and much more qualitative rather than quantitative. She went and sat down with students and had the students think aloud as they solved these problems. And it was on that basis that Donna and I were able to map what we were seeing in the students' thinking to Piagetian theory. I have to address an elephant in the room in case there are some people with a good, strong education background out there. The odds are that you've been taught in your education about education that Piaget is dead. Well, Jean Piaget is certainly dead. He died in the early 1980s, but furthermore, his theory is dead. And it's certainly true, and I'm not going to go into the details, that significant portions of Piaget's theory are now discredited. We Neo-Piagetians, and remember, I didn't invent Neo-Piaget. I am now a converted Neo-Piagetian evangelist, but we Neo-Piagetians believe that we've salvaged all the good bits, and we've thrown away the bad bits. And I could talk for a long time about why some things are good and why things are bad. I'm not going to. I will make one very important point, which is in classical Piagetian theory by Jean Piaget. He's talking about the development of kids. So he talks about how kids reason at 2 years of age, how kids reason then change at around 7 years of age, how they change again at 12 years of age, and so on. That's not what Neo-Piagetians do. What we say is, no, it's not really biological. It's not only biological. It's not the developmental stages of a child. What you see in the Piagetian stages is something you see when a person of any age learns something new. It could be computer programming, it could be chess, it could be anything. You will see these levels. And I'll show you what that means in programming in just a second. If anybody's still very unhappy with me, what I'm trying to do here is show you that I am aware that Piaget has its critics and its good critics. If people still want to debate that with me, we'll do it another time, please. Okay, so here are what we call the 3 stages of the novice program, and here I'm using the 3 terms straight out of Piaget. The student goes through 3 stages of learning to program: sensory motor, pre-operational, and concrete operational. I'm not going to go into great details about how I justify mapping these from Piaget literature to programmers, but I'm going to summarize the mapping I've made. And that is, students in the sensory motor stage can't trace. And furthermore, their approach to programming is just incoherent. You must have had the experience of sitting, you're just looking over the shoulder of some student as they try to write some code, and it's just incoherent. You cannot see a thinking process as you watch them, change their code. There just doesn't seem to be any sort of thinking process behind it. There certainly are students, particularly students who can't trace. I mean, if you can't trace, you can't do anything. Your approach to programming will be chaotic. You may be pleased to know I'm not going to say much more about tracing today. I'm going to talk beyond that. The pre-operational are the ones that really Donna and I found most interesting, and that's what I'm going to talk about mostly. These are students who can only trace. And like the person who has a hammer, every problem looks like a nail to the pre-operational student. Every problem in programming is solved by tracing code. I'll elaborate upon what I mean by that shortly. I just want to talk about the 3rd level. And the concrete operation level in Piaget words is basically how most teachers assume that students think. And certainly for the first 10 years or so of arguably the first 15 to 20 years of my teaching, I thought students thought the same way that I do about code. And I was wrong. I eventually learned through all this research that I was quite wrong, that all students think the same way that I do. That there's these other 2 categories of how students think about code. And I won't say much about that 3rd category either, because that's the sort of assumptions you already make about your students. And here's the preview, the takeaway message, and that'll frame everything else. The key idea that comes out of this Piagetian thinking is that we assume that students, there are 3 stages, and we assume, however, in our teaching that students really start at stage 3, or effectively they move so fast through the first 2 stages, sensory motor and pre-operational, that they end up almost immediately thinking at stage 3. And so we talk to the students the way we think about programs. We, the teachers, talk to the students in our lecture series about how we think about a program. And for all the students, and that's fine for the students who are at that 3rd stage, but for all these students in the lower 2 categories, we might as well be talking to a foreign language, and in a strong sense we are. They don't understand our language. They haven't got to the point yet, the 3rd stage, where they can understand our language. Now, oh yes, what am I doing? Piagetian theory can be confusing, and one of its unnecessary ways for it to be confusing in this talk today is that these 3 words, I don't want you to end up spending the rest of the talk struggling to remember these 3 terms: sensory motor, pre-operational, and concrete operational, and what order they occur in. That would be a cognitive load you don't need. So I frequently use 3 other words to describe these 3 stages, and here they are. Well, not words, but terms. I talk about pre-tracing students. They can't trace. They haven't learned to trace yet. I talk about tracing students. The only thing they can do is trace. And finally, I talk about post-tracing students, students who've moved on from, they can still trace, but they've moved on to reason about code in a more abstract way. Now, I've discovered recently that as convenient as these 3 terms are, pre-tracing, tracing, and post-tracing, I've now found that when I talk to people, they forget Piagetian theory entirely, that this has origins in Piagetian theory, and they just think purely in terms of those 3 things. And some of the things I'm going to say will be assertions that don't make sense unless you remember that I'm drawing them out from the Piagetian theory. Okay, so pre-tracing, tracing, and post-tracing can't be too hard to remember, I'm pretty sure. Well, I hope so. So I'm not going to say very much at all, because I've hammered to death the pre-tracing students on Monday and Tuesday. I just remind you again, and maybe you should stick this on your wall above your office, above your desk. We did this multi-institutional study with 12 universities, 7 countries, lots of students, and an awful lot of students were scoring, half the students were scoring half or less on our 12 multiple choice questions. They can't trace, they can't do very much at all. That's all I'm going to say about those students, I think. In fact, because I wanted to shorten my talk, I think, yeah, I've done this. I put some big lines through some of my slides. It's the last thing I did before we started today's session, to say to myself, Raymond, don't talk about this. You've talked about this enough. I could talk for hours more about this, but I'm not going to. I will, however, break the rule for one thing. I would like to compliment James' presentation yesterday on many things, including his use of these tangible things like cups and so on. Students who can't trace need these sorts of props to understand how programs work. So nice work, James. That's all I'm going to say about that. I have talked about this before. It's a lesson that students, even at the end of high school, and for that matter, even at the end of first semester at university, cannot solve, well, many students can't solve very simple tracing problems. So I'm going to skip that. Phew, well done. I got past that, and now I've got past the students who can't trace, and I want to talk for a while about the students who can. But here's the key, and this is what only came from knowing Piaget literature, neo-Piaget literature, and Donna's Think Alouds. I didn't know these students existed until Donna came into my office and started talking about them. By this stage, you know, I'd been teaching for 15 years, and I didn't realize this was going on in my students just from my teaching. It was only when Donna sat down with students and had them solve some problems by thinking out loud that I began to realize that this was going on amongst the students. Now, okay, before I go any, there's an anecdote comes to mind, a quick one, which I must tell you, because I want to advocate for doing research again. And that is, you know, I've said before, particularly yesterday, you know, sometimes you've got to take a step back from your teaching, and you've just got to watch the students. And from what you observe, you learn something new about them, and that improves your teaching. The trouble with being a teacher all the time was, it's not exactly trouble, but, you know, a teacher will always intervene to teach. And when Donna started her Think Aloud work, I had to sort of coach her for a while, because she was a teacher of many years' experience. And as soon as the students started to get off track and answer the questions incorrectly, Donna, the teacher, would jump in and correct the students. And I would listen to the tape recordings that Donna had done of her Think Alouds, and I'd be listening away, and I go, no, Donna, no, Donna, you can't stop the student and correct them. We're here to observe the student. Now, at the end of the Think Aloud hour, if you would then want to be Donna the teacher and correct the student, by all means, but for that hour, you must just listen to the student. Don't teach them, just listen and observe. And from her listening and her observing, I learned something about my students that I hadn't learned for 15 years, after 15 years of teaching. So these are students who can only trace. And I want to illustrate that by talking about a student called Donald, who did something that we found fascinating and astonishing. So this is the problem we gave Donald. In one sentence, describe the purpose of the following code. Do not give a line-by-line description. And I'm going to work you through it so that you understand the code. This is not all the code. We're going to add some in a second. So if y1, a variable called y1, is less than the value in y1 is less than the value in variable y2. And then we didn't give the student code because we didn't want them worrying about how a swap worked. We just gave them the pseudocode effectively. There would, if this if condition is true, then there would be code to swap the values in y1 and y2. That would go there. So if I asked you to describe just that code, and if we were in a room together, I would at this point stop and insist that somebody tells me, just if nothing else, to wake up the room. No disrespect intended, but I'm a terrible audience member at most presentations. I kind of switch off very easily myself in many presentations. So if we were going to describe what that code did, there's an answer. It rearranges the values, if necessary, rearranges the values in y1 and y2 so that the smallest value is in y2. Okay, so the smallest value is in y2. T to be in y2. Now I want to focus on this bit of code, which is almost the same as the previous code, but instead of y1, y2, it's now y2 and y3. Same idea though. If the value in y2 is less than the value in y3, swap those two values. So if I now ask you what happens as a result of executing those two if statements, your answer might be it rearranges the values if necessary so that the smallest value of the three values is now in y3. And I've left out because I didn't want to fill up the slide too much. Of course, the other two values are in y1 and y2. But bottom line is I'll give you full marks on the exam paper if you said it rearranges the values so that the smallest value is in y3. And then finally, the last piece of code is a repeat of the first piece. So we've compared y1 and y2, and if necessary, swap the values. We've compared y2 and y3 and necessary swap the values. So we now know for sure that the smallest value is in y3. And then we compare y1 and y2 again and swap them if necessary. So what are these three if statements doing? They're sorting the values. On the exam paper, if you just wrote it sorts the values, I'd be happy. We didn't care because it was exam conditions and people make all sorts of mistakes in the exams. We didn't care whether you suggested it might be from lowest to highest or highest to lowest, or we didn't say either. We were just happy if you saw the forest and not the trees and you said it sorts the values. It's a kind of a bubble sort on three elements, really, three values. Now, this is not a trivial problem, we discovered. At my university, I put this question into a mid-semester test, so after 6 or 7 weeks of learning to code, and half my students got it wrong. They didn't give me an answer like that. They couldn't give me an answer like that. Now I felt bad about that, but I felt better when we gave the question to a set of students at another university, and at this point I shall very quietly say it was Donna's university. Donna was a teacher at a different university. And this was in their end of first semester exam, at the end of semester, and 2/3 of her students got it wrong. So this is not a trivial question. If you're worried about the way we framed it and do students understand what's really required of them, let me just tell you that we went to a lot of trouble to make sure that students did understand. I'm not giving you everything. I'm just trying to fit something on one slide. So there's extra stuff not given. Also, we gave students questions prior to the exam to practice questions, which include this. So they should have been well aware of what was required of them. So what we just did, working through that code and coming to the answer that it sorts the values, is what I'm going to say is a post-tracing reasoning process. We didn't read the code with a specific value in mind for y1 and a specific value for y2 and a specific value for y3 in mind. We read the code in an abstract way. Being experienced programmers, we were able to say, if you execute that code, then the smallest value will be in y1 after it. And if you execute all of it, the smallest value will be in the values will be sorted. We didn't think in terms of specific values. So it's not tracing, it's post-tracing. You might argue that in a sense what we did was tracing. In a very abstract way, we were tracing. We weren't so much keeping specific values in mind in y1, y2, and y3, but we were keeping sort of constraints in mind. We knew that after we'd done that, after the first line, there was a constraint on the value of y2 that it must be smaller than the value in y1, or equal to, for that matter. But let's not get into that. So you might argue it was a very abstract form of a trace without specific values. Okay, that's fine. If you want to call the post-tracing stage the abstract tracing stage, that's fine. But nevertheless, they're not tracing with specific values. And I will describe what we just did as a deductive process where we figured out what the code did by just reading the code. The deductive process. It turns out that the tracing, by the way, for any Piagetians who are out there or Piaget critics, what I just did was an exercise in transitive inference. That's how Don and I dreamt up this problem. It's transitive inference. That will mean something to any Piagetians out there. Don't worry if it doesn't mean anything to you. Now, the tracing students can't do that. They can't reason the way that we just reasoned. They have no other skill other than tracing. And as I said, like the man with a hammer, every problem is a nail. If the tracing is the only skill I have, they cannot abstract from the code itself to reason at a higher level. They will attempt to solve a problem like that one by tracing. And that's what one of Don's good research practice, Donald adopted a pseudonym for the lengthy set of studies that he did with us. Here's how Donald went about the problem. There's the code, exactly the same code as before, just now shortened so it's on the left-hand side of the page. This is what Donald did. Donald said, y1, y2, y3. He initialized them to the values 1, 2, and 3, and then he commenced to trace. And I will point out, I will boast at this point that when Donna and I devised this question, we gave the variables the names y1, y2, y3, because we were hoping that some student would do this, initialize the values to 1, 2, and 3. Okay, and then Donald did a perfectly well-organized trace and quickly and efficiently, and he correctly traced to establish that the value in y1 at the end of this would be 3, the value in y2 was 2, and the value in y3 was 1. A correct trace. But here's the fun part. Donald is not a post-tracing student. Donald is a tracing stage student. He cannot reason from code. He reasons inductively from the values. He started with 1, 2, 3 in his 3 variables. He finished with 3, 2, 1, and he could have made the correct deduction from there, but he did not. His induction of what this code did was the following. It reversed the values in those three variables, y1, y2, y3. Not that it sorted them, it reversed them. Now, I remember when Donna came to my office and said, "You'll never guess what Donald did." And I listened to the tape, and Donna and I sat around for quite a while going, but that's amazing. For example, I can remember I said to Donna, well, to begin with, if all you're doing is reversing values, you don't need if statements. So why does he think the if statements are there? And furthermore, if you're trying to reverse the 3 values, you don't need to worry about y2 at all. You could just compare, you could just swap y1 and y3, which is in fact not an operation that we offered here. So all up, pretty clearly, Donald is not thinking at a post-tracing level. He's not really thinking about the code. He's thinking at that tracing level where purely deductively, he's doing that. And coming up, because we constructed it this way, he's coming up with the wrong answer. We wanted to find out to students who do this sort of thing. Now, a little side note, I should have had something about this. I talked about explaining plain English questions and how you can use them to study students and what they know. If you're putting explaining plain English questions into your exam, be careful that the student can't figure it out this way by tracing, by picking 3 values and just tracing and then inductively figuring out what the code does. Well, you can do that, but what you're really trying to do with an explaining plain English question is give them code which works at the post, where they have to reason at the post-tracing level to figure it out. If you go back to the one that I looked at yesterday, where the code checks to see if an entire array is sorted, you'll see that the odds are that you will not figure that out just by tracing some random values. You need to think harder about the code. Okay. So that's what Donald did. I don't know if you're surprised that Donald did that. I was astonished. And this is more than 15 years after I started teaching. Now, during talk 1 on Monday, Tanya, and I will not mispronounce the rest of her name, Tanya said in the chat window, "I've taught learners who are terrible at coding, and later on they've become programmers in industry." Yes, Tanya. In fact, this is a digression in a sense. Yes, Donald, in fact, went on to work in industry quite well, as a matter of fact. He was regarded by his teacher at the time as a student who was not doing well in the programming undergraduate course. But Donald went on to work in industry. And the moral of that story is, with some students, teachers need to be more patient. Well, furthermore, you don't move a student, but give them developmentally appropriate learning tasks. What I mean by that is, if you give a student like Donald, who's at the tracing stage, a large program to write, or even a small one for that matter, they don't learn anything. They just resort to bad programming practice, and I'll show you some bad programming practices in a second. They don't learn anything as a result. You've got to give tasks to the student that will help them develop from the tracing to the post-tracing stage. And it's really only when a student gets to the post-tracing stage that you can expect to see them write code using a sort of a coherent thinking process. Before the post-tracing stage, their approach will be somewhat chaotic. So, yes, Donald went on to work in industry. We need to teach more slowly, be more patient, and in particular, we need to give developmentally appropriate learning tasks. If we just write a program to do X, write a program to do Y, and if that's how our teaching is done, the students at those first 2 levels will never progress to the 3rd level. The 3rd level students will be just fine, but those other 2 levels are stuck. Now, for the tracing stage student like Donald, there is little or no abstraction beyond the code itself. All Donald and others tracing stage students can do is trace code and then make inductive guesses, if you like, about what the code does. And bear this in mind, because now when you go into your lab and you look over a student's shoulder and you see them doing bizarre things, you may understand why, because they're like Donald. They don't abstract. They don't see the bigger picture, the abstract picture. All they see is executing code. Now, programming by random permutation, I left that word out. This is such a well-known thing that somebody felt they needed to have a Wikipedia page about it. This approach sometimes seems attractive when the program does not fully understand the code. Happens in industry, so I'm told as well, but I'm more focused on students. I certainly see no end of students randomly changing their code because, in fact, they don't understand the code. Related to that is shotgun debugging. They've written some code and they've run it and it doesn't seem to work. So because if they're reasoning at that tracing stage, if they haven't moved up to the third stage, well, they have no way of debugging their code beyond making some relatively undirected changes and hoping that eventually they'll get it right. And for very small problems, 5-10 lines of code, maybe they do get it working. But it's a process that will not work as they move on to more larger exercises. Voodoo programs is a favorite term of mine. Even if the program works, the student does not understand why it works. I've certainly had those encounters. I've had students come to me and when I ask them about their code, it turns out that even if the program works, they don't seem to understand it. And in my early years of teaching, well, actually until relatively recently, I just assumed if a student had a working program and they couldn't answer some simple questions about it, that they obviously got somebody else to write it for them. And maybe they did. I'm not eliminating that option. But I now know that, in fact, particularly on small exercises, the student might have got it to work, but they actually may not understand why it worked. I mean, if enough monkeys type long enough, eventually they'll type Hamlet. And if a novice programmer keeps typing long enough, eventually they'll get your small programming exercise to work, but they won't understand why. Oh, a little detail. I know maybe I could skip over this. How am I going for time? Not bad. Not bad. Maybe you don't need this. This might be more for the people who know Piaget. One of the problems with classical Piagetian theory is Piaget talked about those three levels: sensory, motor, pre-operational, concrete operational, which I'm mapping to pre-tracing, tracing, and post-tracing. And there's always been this worry in classical Piagetian theory about how do these students appear to make these quantum leaps from one lower level way of reasoning to another? Why does a 7-year-old suddenly switch from one sort of reasoning to another? Are they struck by lightning, or what is it? Well, neo-Piagetians think they have the answer. And it's rather than sudden quantum mechanical like transitions, the students are steadily making changes. That is, I've drawn time on the horizontal axis. When a student starts out, they may move very quickly to more sophisticated ways of reasoning, but every student, the first instant they're exposed to programming, they're in the pre-tracing stage. That's their dominant activity. That's how they don't understand how code works. They can't trace it for that reason. For all sorts of reasons, students can't trace. So, but as they begin to learn some stuff, that sort of pre-tracing behavior, errors in tracing and errors in reasoning about programs, misconceptions about how assignment statements work, how while loops work, and so on, they decrease with time, and the second type of reasoning increases, so that eventually the dominant way that the student thinks about things is what I call the tracing stage, like Donald. And then as time goes on, hopefully, particularly if you give the students developmentally appropriate learning tasks, if you throw them in the deep, if you throw Donald and other tracing students in at the deep end with lots of writing of quite sophisticated programs, they'll not progress beyond this stage. But if you give developmentally appropriate tasks to the students, they will eventually rely less on tracing their code and more upon reasoning about the way that you and I do, and they will move to that post-tracing stage. So you can see students in your class that clearly fit into those three categories, but you'll find lots of students also who are not easily mapped into those three categories. Donald, at that instant we caught him for that Think Aloud session, was very much a tracing student. Yeah. So the three stages of the novice program. Can't trace, can only trace. That's the ones that we've been talking about. I want to make you aware of this, the students who can trace but they can't do anything else, because I think they are the neglected category. We are aware that students can't trace. We are aware that students have misconceptions about how an assignment statement works or a while loop. That's well known, but I think this is not so well known. That there are students who don't have misconceptions and so on, but they can only trace. They haven't really abstracted yet to how the code works. Which brings me to the conclusion to part one at the top of the hour. This is brilliant. 3 stages of the novice programmer. Well, I'll just leave that there for decoration. I've been talking about it for half an hour. I don't think there's much to add to that unless when I hit the space button, something else comes up. Oh, it does. Teachers commonly assume that novice programmers start at stage 3, or at least get to stage 3 easily and quickly. That is not the case, at least for some students. Perhaps many students do. I'm in no position to put labels on, what percentage of students are in these various stages. I suspect that this is the tracing stage students, and well, that matter pre-tracing, but let's stick to tracing. I suspect there's a lot of students in most classes who are at this stage. But the reason why a lot of students are at this stage is not because of anything to do with them. It's because we're not giving them learning tasks which are intended to move them from that stage to the next stage. If you ask students at this stage to write large programs, they will go about it in a very bad way, and they will not really learn much. And they'll just stay there they'll just stay there. By the way, Donald went on to work in industry. I have to say that I think Donald went on to work in industry, because he got into our research program, and Donna did. After she'd spent an hour talking to Donald and watching him make a mess about things, she would then spend teaching time with Donald afterwards and say, no, Donald, this is what you're doing wrong, and explain it to him. And Donald did eventually go on, and I don't think he would have in the traditional undergraduate program at Donna's university. I don't think he could have gone on to become a programmer, because the traditional undergraduate program wasn't catering to a student like Donald. Now, that is, if you like, the first half of talk 3. And I can go on to talk about teaching practice, which, let me say, is related to Piagetian theory, because you may see the influence of the Piagetian theory and the idea that there are tracing stage students who have problems. You may see that, or you may not. There is a connection in my mind, maybe there isn't. But this is the point where I shall ask the organisers, should I carry on? Let me show you before you have to make such a call.
Sorry, Prof, can we just do questions on the first talk before we continue?
Absolutely. Before we do that, absolutely, that's a good idea. I'll just give you an indication that is slide. Okay, so I'll be starting at slide 38. No, sorry, 38. And what I have, if I go through all of them, don't necessarily have to go through all of them, is well, that's the last one really. So 48. There's another 15 or so slides. So that's for your information. But no, let's go back to let's take the questions then.
Okay, Prof, one question we've got is, what are some of the tasks you mentioned to help the students move from stage 2 to stage 3?
Yeah. A lot of patience and repetition, I think, is what you've got to do is, as they perform a trace, you've got to relate the trace to, say, a diagram of what's happening in the code. Well, for that matter, it could be, it could be paper cups with numbers in them, as was being demonstrated yesterday. So you've got to relate the code they're looking at to the to that abstraction, that symbolic simulation, if you like, of the code. And you can get them to do it. I mean, you can say, okay, you've just changed, you just executed, successfully traced this line, in the code. What did that do to your, what did that do to the values now paper cups, or they then have to do that. Now, to be precise, when I talk about stage 2 and stage 3 programmers, there are people who can trace code. Yep. And even many of those people, if you show them the simulation, if you give them a bunch of things and say, sort them into order of size, they can do it. So in that sense, they understand at an abstract level how to sort. But what they can't do is connect the abstract level, the physical thing they just manipulated, to code. It's that disconnection between the two that we're working on. And what I have done many times with students, particularly when they come to me with buggy code, is we sit down and we have a sort of I pick up a few items off my desk and I arrange them. If it's a sorting algorithm, just to give a simple example, and we work through their code line by line and say, okay, what did that do to the objects sitting on my table? Move them to show me what that line of code just did. And then I say to them, is that what you wanted the code to do? So that's the primary one. It's practice at seeing the connection. Yeah, don't take it for granted. And you might say, well, in my lectures I do that all the time. I have diagrams on my slides and I show. Yeah, but hang on, just because we do that at the front of the lecture theatre, I know this is I'm not being patronising. You know this, but there are people who don't know this. There are people not attending who don't come to seminars like this who don't know. Just because we say something at the front of the room doesn't mean students understand it. And furthermore, you need the students to manipulate the symbolic constructions themselves. It can't be you doing it at the front. It's got to be them doing the manipulations, and somebody telling them where they got it right or wrong. That's the best I can do right now. This is actually a pretty open area. Improving students in this area, I think, is, I mean, unplugged, the unplugged stuff, and also, you know, that I know CS Unplugged from the person in New Zealand who does a lot of it. I'm not sure if it's close related to what goes on in South Africa or not. That's great stuff. I like it. Don't get me wrong. I don't like it. I do like it. But if I go back to this for a second, a student can possibly manipulate, you know, a CS Unplugged exercise, right? Like sorting values or something like that, right? And they might be able to trace code that does the same thing, but they don't actually quite see the connection between the two. And that's what you've got to work on, is connecting the high level picture to the code. Long answer. I hope it wasn't too long. Anybody else?
It's a long answer, but a very good answer. Prof, there's not specific another one in the chat, but there's somebody with a hand. Brandon, you can ask your question.
Sorry, can you hear me clearly?
I can hear you. Yeah.
So like, I'm an IT teacher in a high school, and I'm just from my personal experience when I did IT at school. I tell my students, like, there's a thing like sometimes in programming where I call it the aha moment, when it all clicks.
Yep.
And at school level, like we in grade 10, 11, and 12, like at grade 10, 11, I struggled to get that aha moment. I literally got it late in my final year of school. But what I did to survive in the subject was to look at the parts that I like to get the marks, or to be able to do things that I could do. So like the theoretical aspects, I focused on that just to keep me, like I tell the students, to keep me in the game. And so what I try to do with a lot of particularly my weaker students, is I try to tell them there are what I call recipe codes. There are things where you can learn particular recipes, and those are the algorithms, like your sorting algorithms and so on, that are that the kids can at least see how that works, and they can play around with that code. It's like if you were learning to cook. You don't learn how to bake. You don't experiment straight away. You first start off with generic recipes of how to do a scone or how to do brownies and that, and you learn like that before you start experimenting with your own styles. So I found, particularly with my weaker students, just to give them that to still ignite that love for coding, to see that I made a computer do a sort. Even though they use someone else's code technically, but for them to see that, and then they can play around with it. So I feel like for our weaker students, I often use, as I said, like a recipe code that they can at least see how it works. They can like play around with it. They can still dabble with coding until they get that aha moment where it starts to make sense.
I agree completely with you. In fact, you've just cheered me up tremendously, because I was heading into this second section on teaching practice with a little bit of trepidation, because I think what I'm going to present is not fashionable. In that I agree with you. I give students quite a lot of code, and I get them to know it. But that sounds like rote learning to many people, and I will talk about why I think you can avoid rote learning. But I agree with you absolutely 100%. I mean, what you've got to do is, there are three things. The students, first, the students got to be able to trace. You've got to get them to the point where they can trace. You've got to fix the misconceptions and so on. There's no point in really showing them any code until they can trace. Okay. Then you can also show them the high level algorithm where they do it, like CS Unplugged. They put objects in front of them and they manipulate the objects, so they understand the algorithm. But the third thing is what we take for granted. We think that students relate those two things, the code, which they can trace, and that high level simulation. They don't. It can take time for that to happen. And the best connection that I can think of in education literature in general is the literature on reading. Kids learning to read. There are kids who can stand up with the book and quite fluently read you a paragraph or a page, and then they can't tell you a thing about what was in that page. If there's any teachers who used to teach in primary schools, and so they will be aware of that, I think. And this is exactly the same thing. There are students who can trace code, but they can't really tell you a thing about what the code is doing. Okay, is that an answer? We've agreed.
No.
This is
Just a little comment. Yeah. I understand the whole concept of road movement. Just for a lot of our students, like for the weaker ones, just to give them the time that they need to get that aha moment, like just to play around with it, just to get them there.
The aha. I agree with the aha moments. I'll go back up. Am I still on screen share? Can you see my overlapping waves again?
Yep.
Yeah, I almost gave you a second slide after this, but I decided it might be too much information. But now that you've brought this up, this whole idea of aha, I think the neo-Piagetians might overstate slightly the overlapping waves. I think that what goes on is, I was going to have a picture of a kettle. You turn on the kettle, and at 70 degrees, 80 degrees Celsius, 90 degrees Celsius, you've got water. At 99 degrees, you've got water. But suddenly at 100 degrees, the water starts turning into water vapor, right? You get what's called, the physicists would call a phase change. And I think we do see that some of the times for students. The aha moment is when suddenly they stop being predominantly pre-tracing and they switch. There's this moment where it all comes, as you said, it clicks. The pieces suddenly come together and there's a phase change in the way they're thinking. So yes, I believe in aha moments too.
Cool, thank you.
Anything else?
No, just a comment. Thank you.
Great.
Thanks, Prof. We also just got one comment. It might also differ per topic. That means depending on the topic, things might change. Do you want to comment on that?
Absolutely. It's a good point. If I was talking for much longer about Piagetian theory, we would talk about the Piagetian principles of assimilation and accommodation. So that sometimes, I've taught you for a week on integers, and all we've talked about is variables, and we've moved integer values around amongst integer variables. Then I come back in next week and I present you with floating point numbers. And really, there's still values moving around between variables. I'll give you very similar tracing problems to do, and there's no difference because there's a difference in that we're now working with floating point numbers, but the principle of how to trace and so on hasn't changed. But then sometimes concepts come along which disrupt your way of thinking. And an obvious example that most people are aware of is when you introduce loops. Suddenly students' ways of thinking about code kind of break and they struggle for a while. Sometimes things move smoothly and then sometimes there's a real break and a change. Is that what the person was getting at with the question?
I think so. I think that is what it is, that sometimes it's not that easy to do it that way. But in that case, if we look at what James showed us yesterday, I think that was a very good idea to show students how the changes are. It is a type of tracing, if I'm correct. It is type of tracing, but more visual than writing down.
Yep.